This is a lesson on spectroscopy. It's basically the study of the splitting of light into its constituent colors, into its constituent wavelengths. For example, through the use of white light and a glass prism. A very simple setup. So a spectrum, by definition, is simply a band of colors produced when a light is passed through a dispersive object such as a prism. We've all seen this effect. If you have, let's say, a glass ornament on a table and light passes through the door or window in your living room, let's say, and it hits the piece of glass, the glass ornament, you'll typically see like a rainbow on the table if it's on a table. Okay, so the splitting of white light into its constituent colors is called dispersion. This was a concept explored in Year 11 physics, dispersion. So it's when white light, or denoted with W, splits into its constituent colors. So Roy, G, Biv. Red, orange, yellow, green, blue, indigo, violet. It's pretty useful to know for the HSC. So there's an instrument called a spectrometer that's used to study the spectra of elements. So spectra is plural for spectrum. Spectrum is singular. Quite a simple setup. You can make a spectrometer as follows. Suppose you have, let's say you have like a heated gas, I should say, take a incandescent light bulb, okay, that produces white light, very badly drawn light bulb, and you pass that light through a glass prism. What happens is you'll get a rainbow. So the Roy G Biv colors, okay, through some observation screen. Roy G Biv, okay, which is what you see with your eye. So our eyes can detect visible light, okay, only a small part of the electromagnetic spectrum, from around 400 to 700 nanometers. So spectra come in three main types. The first is an obvious one. We're all familiar with this from everyday life. It's what's called a continuous spectrum. And this is basically EM radiation, electromagnetic radiation, with a continuous range of frequencies, hence continuous spectrum. Okay, so you get all the visible wavelengths of light, okay, in the electromagnetic spectrum. For example, e.g. light from the sun and light from an incandescent bulb, as I mentioned before. So quite simply, take an incandescent bulb and typically a spectrometer involves a slit. Okay, slit only samples some of the light going through. Okay, spectrometer doesn't really need a lot of light to operate. So it samples a bit of light, so white light in this case from the light bulb, hits a slit, only some goes through. Okay, so there's lots of light coming out of it, but we only want a bit of it. Hits a glass prism, typically. You get Roy G Biv coming out, Roy G Biv, the rainbow, colors of the rainbow, and what you'll see is a continuous visible spectrum. This is also known as black body radiation. More on this a bit later. So the intensity of the emitted EM radiation increases. So intensity increases, and the wavelength of the maximum emission decreases as the temperature, as temp of black body increases. So this is basically saying that if you heat up an object, basically it's the light intensity increases, right? It gets more and more bright. And the wavelength of the maximum emission decreases. There's a particular wavelength which corresponds to the high intensity. That's got a short wavelength, okay? High energy. So a black body, by definition, and I'll talk about this a bit later in another video, is an object that absorbs all light that falls on it and reflects none. So it's a perfect absorber of light. Okay, that's a continuous spectrum, otherwise known as a black body spectrum. Number two, you have what's called an emission spectrum. And we're also familiar with this if we look at street lamps at night. So when you have an excited could mean thermally or electrically. So excited, okay, e.g. thermally, so through heat, through action of heat, or electrically, okay, via electricity. So an excited gas emits electromagnetic radiation, EMR, at very specific wavelengths. Okay, turns out that different elements on the periodic table emit different colors of light. Okay, they've got their own unique sort of fingerprint, think of it that way, fingerprint spectrum. And so this is really useful because you can use what's called flame spectroscopy. Flame spectroscopy for chemical analysis, okay, which is pretty useful in things like forensics. You want to determine what elements are present in a sample. For identifying specific elements, okay, in a gas or vapor sample. Okay, you can vaporize a sample that's suspected of containing some elements, and you can then study its spectra from that. Fireworks are great examples. Fireworks are made of transition metals on the periodic table, things like copper, barium, and different colored fireworks. There are different colored fireworks because there's different types of elements present basically in the fireworks. Okay, so they emit emission spectra due to excited metal atoms, okay, to produce specific colors of light. Okay, the reds that we see, okay, from strontium, the element strontium, the bluish green from copper, for example, and so on and so forth. And it's basically what we had before. And also I should mention sodium street lamps. Whenever you drive by at night and you look at street lamps that are emitting yellow light, they're made of sodium. Sodium emits yellow light, has an emission spectrum in the yellow part of the visible spectrum. It's quite a simple setup. You have a heated gas, so typically, I should say excited, doesn't have to be heated. You have an excited gas, pass that through a slit once again, and the slit will sample only a bit of that light. You have a glass prism, and what you'll see is, on the observation screen, very specific colors of light. Okay, let's call this element X. So you'll see bright lines along a black background. Okay, because the element X in this case only emits light at those particular wavelengths, those particular colors, and not at any other wavelength. That's why the background's black. And the last type of spectrum is called an absorption spectrum. So this occurs when you've got a continuous spectrum sent through an unexcited gas. Okay, and this gas absorbs the same unique wavelengths that it emits when excited, okay? And it leaves dark lines in the spectrum. So suppose you have some energy source and you give it to a cool gas. Okay, that cool gas will then get excited, and through a slit, through a prism, and out what you'll get is, you will find dark lines with a colored background. So these are dark lines, not bright lines. Okay, the gas, the element in this case absorbs, as I mentioned, particular wavelengths that it emits when excited, okay? So that's an absorption spectrum. An example is when starlight passes through a cool gas cloud out in space. And so these are the three main types of spectra. You've got continuous spectra. We've got this continuous range of different colors, frequencies. You've got an emission spectra, where you've got elements giving off specific colors of light, bright lines of colored light on a dark background, black background. And an absorption spectrum, we've got dark lines accompanied by a colorful background.